Thank you very much. Welcome to my talk. Thanks to the organizers, of course, for hosting this. I back up James saying that it's a lot of work, it's a lot of energy, so thanks once again. So as the chairman said, I will be talking about the dynamical formation of spin glasses in a peculiar case of cavity QED experiments. And basically, I will be focusing in particular on the role of fluctuations. So how much quantum mechanics you need in these experiments to synthesize a spin glass starting from a totally uncorrelated state. And before moving on, I should give credit to collaboration to Derek, which unfortunately is not yet here, stuck in the air traffic all over the world, and to Hossein Abadi, who is a crazy good student that I have in Mainz, and is the mastermind behind this, and unfortunately could not join due to visa issues. And as you probably have seen from the program, there is a closely related talk, which is actually the experiment that motivated us by Benjamin Lev. So that's a beautiful example of accidental coordination in physics. So we came out in the same month from the archive without knowing about it. And in actuality, this is going to mirror in my talk because I will be presenting results about a model that is inspired by the experiment, but actually there are some quantitative differences with respect to it, okay? And I will try to point it out so you are ready tomorrow to have more fun with Ben. All right, I think I said everything I wanted to say, so maybe you're in this room and you don't care about spin glasses, or maybe you don't mind about cavity QED, so I want to motivate you with a general physics question. Let's say I give you an interacting many-body spin system. That can be in 1D, can be a spin chain, can be in 2D, can be a fully connected situation, okay, maybe a central spin model, like in this cartoon. And now, each of the spin have all the same size, S, but you can choose how big is S. And the question I want to ask you is how big S has to be for the whole system to classicalize? The question is motivated by what you learn in quantum mechanics 1, right? They teach us that essentially 1/2 is very quantum, but when you make S grow, commutation relations start to trivialize and you get back classical rotors, okay? So this answer is clearly non-universal. It's going to depend from geometry, it's going to depend on nature of interactions, and it's going to depend maybe on the dimensionality as well. But that's the leitmotif of my talk, okay? So we need a primer on spin glasses, you like it or not. So I apologize if for some of you this is going to be quite standard, and I like to copy the words of notable predecessors that I have in mind. So basically, the simplest way to understand this is that you have a fully connected spin system, classical spin system. So these SI are just classical variables, okay? Binary classical variables. And you're going to have all-to-all interactions, but these interactions will be disordered. And they will have the property to be sign changing. And so actually this can create frustration. And so what Kurt Binder was saying in this extremely old review now, basically as much as old as I am, that the spin glass transition is a situation in which magnetic moments are in conflict with each other. So you will not generate any type of conventional spin order like ferromagnetism, antiferromagnetism, but rather at a certain point what happens is that you try to cool down the temperature, right? So like in normal phase transition, you are after a critical temperature. But below this critical temperature, you don't get a situation like this, that's conventional Ising order. You're going to rather have a global magnetization that is 0, and this single magnetic moment will start to be stuck, will start to be frozen. Their fluctuations will basically be extremely long. And so the spin glass transition is a transition in dynamical properties, in capability to relax. So it's inherently connected to equilibration. And the canonical way that people do to illustrate to kids how this is gonna be, I mean, it's a cartoon, right? So you have to take it cum grano salis. When you have an Ising transition, you expect below a critical temperature to develop 2 minima. This is spontaneous symmetry breaking. But then in spin glasses, you have frustration, and this gives you a very rugged free energy landscape. That is what you can see in the first cartoon. And you're going to develop plenty of minima that are going to really to explode with system size growing. And actually, the barriers between these two minima grow with system size. So the tunneling will be exponentially suppressed in that, but actually all the spin configurations you may get are thermodynamically not equivalent. So they differ by several spin flips. Each of them is a situation in which the system is stuck in this conflict between magnetic moments that Kurt Binder gives in his review. And if you like, you can look at this from the up. So this is the magnetization phase space. And for instance, you start in one of these islands, and in one of these islands, you want to try to thermalize, you want to try to reach ergodicity. You are in one of these minima of the rugged free energy landscape. But then you are blocked by barriers that are these dark gray regions, and so you try to escape, and maybe you get to one of these other minima. But to be really truly ergodic, you would like to explore all of them, and sooner or later you will be stuck. So basically, the system can relax only in a very long astronomically time scales. So that's essentially the situation. Maybe you have some tunneling, but then you're stuck again. And so basically, true ergodicity never happens for observable time scales. That's the concept of glassiness that you learn at school. So originally, people were talking about disordered magnetic alloys. That's, I think, very old solid-state physics. And I'm trying to make the point that this is connected to ergodicity breaking. And I think all of you are more or less aware that this is very interdisciplinary problem. So it connects to plenty of areas in physics and beyond physics. And that true connection is not just put there. So there are books about how, I don't know, protein folding can be understood using spin glasses models. So this is a big thing. And we Italians like to believe that the Nobel Prize to Parisi was given because of spin glasses. I think the motivation is a little bit more vague, but in any case, it's good to show a Nobel Prize medal. What I'm going to now tell you in the next slide is the second thing you need to know to understand what I'm going to talk about. So that in cavity QD now people can, in a clean way, synthesize spin glasses. And I will not enter in the details of the experiments for two reasons. First, I will be talking about a mockery of the actual experiment. So there are some details that are different. As I said, we were not coordinated, although we came out basically the same week. And second thing, tomorrow you're going to have a talk by Ben Lev about it. All right, so in any case, the basic idea of their experiment, maybe plenty of you know already, is that you have basically an ensemble of atoms. And this ensemble of atoms, there are plenty of them. In my cartoon are these blobs with these blue arrows that are two-level atoms. In practice, these are two hyperfine levels of rubidium-87, and there is the usual double Raman two-photon exchange process that will make atoms talk to each other. I think you got plenty of it. But so tweezers are holding these blobs of atoms, and basically you can control how many of them you're going to store here. Now, in the actual experiment is of the order of 10 to the 5. And in principle, you can try to lower down this number. So I'm going to play a lot with this in my talk to play with the size of the total spin in each of these blobs, which is the number of spins 1/2. So let's say if you have 1, it's spin 1. If you have 10 to the 5 length experiment, you're going to have a huge spin. Okay? And in practice, if you really want to do spin 1/2, the true way you plan to do that, or people plan to do that, nobody has done it yet, is essentially to use a Rydberg blockade. So you use Rydberg atoms, you excite one of these, and the Rydberg atoms prevent all of others to be excited, so effectively you have a spin 1/2 degree of freedom. But what I wanted you to keep in mind is that this is a tunable parameter, and that's the key player of my talk, and this is a multimode that generates multimode cavity. So interactions between these blobs of atoms and light modes are spatial dependent and all uncorrelated from each other. So basically that's a good modeling for disorder. So if you eliminate light, you can imagine the problem to be a network of spin blobs with disordered interactions, with sign changing, frustrating interactions. And so the modes are basically the pathways, the roadways through which these blob of atoms can talk to each other. And that's the question you have to try to guess now in your mind to answer. How big is going to be S to make spin glass formation in this model classical or quantum? It's going to be 2, it's going to be 10, it's going to be 100, it's going to be 1 million. That's the question I will answer for you during the talk, and you can make bets and try to put money on that. And what I want to say is that, besides jokes, a very important parameter, of course, is the number of cavity modes, right? And I think this makes sense. So this ratio is a key guy. And the reason is that if the number of cavity modes is not large enough, you won't have enough roads connecting this blob of atoms. You won't have enough possibility to frustrate spins, right? Because the more are the patterns that connect the spin blobs, and the more you're going to frustrate one guy to stay, let's say, up versus the other stays down, and things like this. So when M grows, when eta grows, you're going to enter the spin glass regime. And I'm going to sketch a cartoon of phase diagram for this problem that, at least at equilibrium, was already known more than 10 years ago. And so that's what I want to say. For eta above a certain critical value, that is roughly order 1, you're going to get the spin glass. So this is just a cartoon of what happens in their experiments. So as you can see, there is a difference. They look from above to arrows, so they have a sort of XY vector model. So that's a little bit different from what I'm going to show in the next slide. But basically, in one sentence, what these people report is that they start from always the same initial condition. They quickly cool it down, so it's non-equilibrium, and they find 4 likely possible configuration of spins. These are these 4 rectangles that you see here. And by looking at correlations between these spin configurations, they can study a very complicated thing in spin glass that is called ultrametricity, and is a notion or a proxy of replica symmetry breaking. But replica symmetry breaking, in loose words, is the fact that you start always from the same condition, and you will land on very different minima of that rugged free energy landscape I was showing at the beginning. Okay, that's enough about the setup. That was just an appetizer, probably. So, as I said, the model that we study is different, but it's a model that somehow plenty of people before us were looking at with very different techniques, and I will summarize this in a second. But so you need to know what I'm trying to solve, right? So, as I said, it's a degenerate multimode cavity, so you have M harmonic oscillators, common frequency omega 0, and now you're going to have the spins that are these blue arrows, and basically you have 2 summations, right? So you have one internal summation lambda that tells you how many spins 1/2 you have here, up to ns, and then you're going to have a summation of Ri that tells you how many of these blobs you have, up to n. And light matter coupling will be modeled to be essentially what I can call a disordered many-body spin boson model. So you have x of light and x of spin talking to each other. And as I said, light matter coupling is independent ensemble by ensemble, so you can approximate this with a disorder thing that's going to be Gaussian with 0 average and finite variance, such that you have a chance to be sign changing and giving frustration to the problem. And naturally, there are going to be photon losses, which are an interesting source of dissipation for what I'm going to talk about. There are also other sources of dissipation. Those are more damaging, and in a sense, from a theoretical point of view, boring, right? So you have to look at things faster before that. But photon losses are going to be very important for my story. So what people do normally in front of a light matter problem of this type is that they like to eliminate the photon. So this basically means you focus on a situation in which photons are very fast, and they're going to mediate instantaneous spin-spin interactions. That's what we call adiabatic elimination in jargon. And what you're going to get are 2 terms. There are going to be intra-cluster interactions. So this is basically the coupling for the same ensemble I squared. So it's going to kill the sign changing nature of disorder, and it's going to give you an LMG model. That's just a little bit more complicated LMG model. And this is going to have a usual paramagnet-ferromagnet transition. But there will be, of course, also intercluster interactions that in adiabatic elimination will look like in this way. And they are between different spin blobs, and the entire game is competing between local ferromagnetism and frustration between the blobs that want to frustrate the system. And in Stanford experiment, I mean, what happens in reality is that you take the actual profile of this G alpha I, you're going to sum over them, and it's going to give you this very funny cosine that is not spatial translational invariant. It is sign changing, and depends from, let's say, the typical width of your cavity mode, and this is where, in actuality, the sign changing thing is coming. Now, the typical question I get at this point, if it was an habit to ask questions to the speaker while speaking, I see that so far we're keeping the style that we ask in the end. People say, oh, what happens if you don't eliminate the photon? We don't eliminate the photon. We solve the problem with active photons, so we don't solve the spin-only or atoms-only model. We do it in the thermodynamic limit. We do it for long times. We keep photon losses, and in particular, we can play with the spin length S. But the funny thing is that if I don't have time, I will not show you how I do it. I will just state what is in the slide. I do non-equilibrium diagrammatics, believe me. And this is because you eventually care about the physics and if the physics makes sense or not. You will not now try to catch me on the technical details. But I have technical slides, and I hope to get there because they are fun. So maybe what this audience doesn't remember or doesn't necessarily know is the history of spin glass dynamics, because now we touch upon that thing. And what you have to remember is that people basically have solved dynamics of spin glasses in saddle point or mean field approximation. There is always some large n parameter, and is a very, let's say, convenient large n parameter that simplifies the math. So the most, let's say, refined version is to go for SUN spin glasses with the n of this SU group to be large. We deal with SU2 spins, and our, let's say, control parameter is the size of the spin in each of these blobs. And this makes diagrams and, in general, the study of quantum fluctuations in dynamics extremely more complicated. So that's essentially where we stand in terms of technical progress. I think somehow it's good to report it, although maybe doesn't resonate a lot with the AMO community. And I would like to go a little bit fast, so you're going to probably believe me. A small light matter coupling, I have a paramagnet if eta is not big. And if G is small, I still get a paramagnet. This is the canonical superradiant transition. I'm going fast here because you are all experts. This is a ferromagnet. In actuality, it's a little bit more interesting than ferromagnetism, but I don't have time to talk about it. And many people have solved this limit before because it's easier than spin glass. Spin glass is here. A strong G and a large eta. And we know this phase diagram because people try to tackle this problem in the 10 years before the experiment was actually done, using qualitative arguments or saddle point. Very recently, Ben Lev group did exact numerics on small samples. I will focus on real-time dynamics that basically for large systems and tunable quantum fluctuations was never addressed before. And I think we can basically get started. So,
can I break the rule? You're asking for it, so.
Yeah, I thought, should I tempt people to do it or not? Yeah, go.
So on the previous slide, you had a kappa in the figure, but not in your phase diagram.
Yes.
And are you characterizing the dissipative steady state, or just to be clear?
I will talk about dynamics, and because it's spin glass, I will never reach an actual steady state. And dissipation, photon loss will be very important. And the omission of kappa here is my missing. So I forgot to put it.
But on the phase diagram?
On the phase diagram, as always, kappa can play the role of a sort of effective temperature. That's, I think, what Sebastian and company were discussing, but they were looking at the steady state many years ago. And I think to get to that steady state, you have to wait really a lot. Maybe you never get there. And actually, I'm going to show you that photon losses are very nice and useful to synthesize spin glasses here. There is breaking a rule now. I'm totally screwed. Go. It was nice before, Professor Speaker. You speak. What is this? 35 minutes, no question. What is that? Disneyland. Go.
Connecting to the first motivation, which is the classical quantum transition. So I don't know anything about spin glasses. So like, what happens in a spin glass that separates it from the quantum to the classical? Like, what would you do as an experiment to know that it is quantum or classical?
It's in general a very rich answer, but it's like the quantum classical phase transition difference. In one case, it will be driven by thermal fluctuations, and in the other case, will be driven by Heisenberg uncertainty. So a quantum spin glass model is like here, something when you have a sigma z field and sigma x frustrated, like in the quantumizing model that we have sigma z and sigma x ordered, and it's
measure something with functional temperature and you see a saturation at some point.
so I intentionally dodged your question because I don't want to give you already the final answer of the talk. I gave you the definition of quantum and classical spin glass, right? Such the book, typical professor answer. The actual thing, how you say that this thing is really quantum or classical, I think is more subtle than that, and you have to wait for the last slide. Cosimo, I don't...
Why are the ferromagnetic and the glass phase mutually exclusive? Or can't the two order parameters, the ferromagnetic and the glass order parameters, coexist?
So you want total magnetization in the system to be zero, to talk about a spin glass.
But you can define just the replica correlator of fluctuations.
You could try to do that, right? But in the more common notion, the idea is that the interactions have killed global magnetization, but still there is some hidden structure. The ferromagnetism dominates, the spin glass will be a correction on top of it. I know what you're talking about. You want to subtract the sigma x non-zero, right? Yeah, sure, you could do that, but then it would not be anymore the dominant thing in dynamics. And actually, I'm going to show you that they coexist in dynamics. I'm going to show you that one fights against the other, and one wants to try to take over the other. It is actually this slide. So maybe you want to hold the question, and I will make you happier than my defensive answer. And now, good. So we start with a very boring state. I think I have to say nothing, that the text is saying it. And actually, the only interesting thing here is that it's easy to know the energy of the initial state, right? Because it will be controlled by the angle θ0 respect to the z-axis. And so this energy is important because if you start with too much initial energy, it may be that you will never see a spin glass, exactly because of what I was saying to Ash, that the effective temperature is a lot, and in absence of photon losses, you will never go into an interesting phase. You will stay a paramagnet. So for the type of state I'm focusing here, θ0 will tell you whether you have a chance to enter spin glass or not. All right, so let's look at what we get. So this is a first plot of magnetization as a function of time. And I am showing you different curves depending on the size of the spin in each of these blobs. And you see, basically when NS is very large, and now I catch up with Sergei, there is a quick decay to a transient ferromagnetic state. So it looks like that this transient is lasting a lot or somehow is stacking you there. And these are the intraferromagnetic interaction, the LMG model, that wants you to ferromagnetize and not make frustrated interaction to kill your MX signal and go to zero as you would like to have a purely dominated physics by spin glasses. Of course, this doesn't mean yet anything, right? Because you want to see more to say that you have a spin glass. And actually, that's my second slide. So you want to first go to zero magnetization, and there you want to see very slow dynamics. And maybe you want to see that when there is ferromagnetism, dynamics is not slow. And that's what I'm going to show you in a second. But I'm showing you this slide for even, let's say, more deep reason. And maybe the question is, if we are nuts. Because like 2 years ago with Anna and my postdoc Shane, we were solving for a very similar problem in TWA. Okay? And then why you bother to do non-equilibrium diagrammatics? And so it turns out that luckily for us now, basically it's all right, of course, when you have large spins. So the 2pi, that is this diagrammatic method, matches with DDWA when the spins are very large, so you see the same behavior. But in DDWA, when you low down the number of spins, so you enter more quantum, the method cannot know, right? Because it's purely semi-classical. It doesn't have this quick fat belly or relaxation to mx equal to 0, typical of small spins, that the diagrammatic method can show. So this is to show that it's legitimate to go for really strong weapons on this problem, right? Otherwise, like, we'll say, okay, you had already the tools 3 years ago, why you bother now? All right. But no, we go back to physics and to understand whether we can talk about spin glass when there is no ferromagnetism and all the things we were discussing with Sergei before. So to characterize a spin glass, you can do many things, some of them very difficult to understand. So for this talk, I'm going to focus on something very simple. It is low dynamics, memory of initial condition, and something that people technically call aging. I'm going to show you in this slide what is aging, and I'm going to show you the spin glasses do age. And that's my way to understand that. I mean, after all, this is a theory talk, right? So I do the quench at time tau 0, and tau, therefore, will be the time I wait after the quench, after I start my non-equilibrium protocol. Now I'm going to measure an equal time correlation function, let's say of the spin. Remember, the photons are active in principle, so it's not anymore true what was told us before, that knowing of photon means you know about spins. They are not enslaved anymore. I'm going to measure them at time separation small t, and that's the object specifically that I'm looking at, if someone that is theory-oriented in the audience wants to know exactly. So you have a spin glass when this correlation function, a very large small t separation, is non-zero. That's a strong memory of what's going on, right? This should not happen. You should not remember, if you measure now and measure 1 million years later, what was happening 1 million years before. But still, the thing remembers. Technically, this is called Edwards-Anderson order parameter. That's the name QEA, but that's a detail. For you is the spin glass order parameter to the right, and I don't think we need to enter in details. Aging means the following. The more the system gets old, and the slower it relaxes. That's also what happens, unfortunately, in human life. The more you get old, the slower, at least motor-wise, you go, right? Hopefully not the mind. So how does this manifest concretely? You see, that's an example of not aging dynamical response. So you have, for different tau times, all curves undistinguishable, and there is just a natural common trend of decay with t, as it should be, as more time passes between the two measurements, and the more you're forgetting. But instead, what is happening to the spin glass, so these are quench parameters of the spin glass, that basically, as you increase tau from bright yellow to purple, the dependence on t gets milder and milder. And that's exactly what I was giving you here. And now, in the leitmotif of the talk, I will show you that this aging is actually weaker when you are going to have quantum fluctuations. So essentially, you see, maybe it's not completely clear from the color code, but trust me, basically these lines are very strong aging for large spins, let's say from 4 to 10. And then when you go down to smaller spins, you have instead a faster decay. That makes sense. So if these things are fluctuating, you can melt the spin glass. Something I haven't told you, because I always forget to put it in the slide, is the role of photon losses that I've celebrated. So photon losses cool down the system. You can start with very energetic initial condition that will prevent spin glass formation if you have no photon losses. But when you have photon losses, you can actually then access spin glass. So photon losses cannot be exaggerated. If they are too strong, you are in this bad cavity limit. Dynamics is massively dissipative. You kill all the Hamiltonian features. But if it is moderate, actually it discharges some energy into the outside during dynamics and allows the formation of spin glass, even if you start with a very high energetic initial state. Okay, I hope you remember my remark at the beginning.
Sorry, can I interrupt you again?
At this point, with this.
It goes back to, the value of kappa, and you said you will stabilize, right? That there is this kind of non-thermalization or slow thermalization that is because of the spin glass formation, but then, of course, kappa on top of that, eventually is going to degrade your spin glass.
So what I am reporting, I am very well aware that is connected also to what Ash was asking. So there was this paper by Sebastian and company. They were looking at the steady state, and their kappa does the usual job of effective temperature in dissipative spin systems. We all agree on that. What I'm saying is that in transient dynamics, kappa is helping me to form the spin glass. I don't know if eventually, if I wait 3 million times, this is going to destroy me. But because basically this is very slow dynamics and nobody will ever get there, I am claiming that dissipation actually is helpful. Photon losses are helpful. You start with a state that is very energetic, and if you run dynamics with no photon loss, you're going to see paramagnet. I do moderate photon loss, I get aging. That's what I'm claiming. I don't have it here, they are in the paper, of course. Okay, so we can get to the $1 million question. So when is the quantum to classical crossover? And now things are subtle, right? We look at the spin glass order parameter, And actually the crossover is basically around spin 2. You don't need to take 3 million, you don't have to take 10, 2. But what I'm saying exactly here, so that gets subtle, right? This is an highly observable dependent statement, as I put here clear in the warning, in the sense, we are saying that if you look at spin glass order parameter, basically fluctuations stop to do damage when spin is 2. It saturates, and regardless how big spin is, it can be 1 million, it can be 9.5, the spin glass order parameter will be the same. If you go for spin 1/2, it's going to be clearly smaller. Now, you may ask the question, is there some hidden coherence? Is this a statement only true for phases of matter, but maybe you have some quantum correlations hidden somewhere at spin 9.5, at spin 11.5? I don't know. I'm happy to discuss any good proxy that people could measure, but that's the way we were taking the problem. And of course, you could ask this also for other phases like this associative memory that is the ferromagnet. I think people are, at the moment, very interested to know how quantum fluctuations can be important there, because again, the experiment is done for very large S. Now, as I said, because you can actually have photons to be active, and maybe you said I have 5, how many I have now? 2. Actually, active photons are something that I will comment after. I wanted to make, let's say, 1 minute comment how we do it, and then I conclude. So, okay, we write down Dyson equations based on diagrams. The way this is done is that you have first to get, so the talk is over, okay, that's my message. Spin equal 2 is the value of spin in which your order parameter doesn't know any more about quantum fluctuations, okay? So that's the end of the physical message. If you don't know what I'm gonna say, it's okay. Now, to put spins on a formal language, you have to do something because they are not good degrees of freedom, they're bad commutation relations. So there is this trick that traces back to, let's say, decades ago, to write down spins as bilinear of Majoranas, and I'm crediting here people that actually did it for this diagrammatic technique 10 years ago. With that tool, you can really make progress now on top of what people built so far for dynamics of spin glasses. So what we have done is that basically we have resumed an infinite class of diagrams. And now I want to guide you through the physics of these diagrams, although maybe it's not fully transparent. So technically what we are doing is what in jargon is called a bubble resummation. So you see, just look at the topology. I mean, 2 bubble, 3 bubble, 4 bubble, so on and so forth. You resume all of this, okay? Now, these diagrams in red are those coming from disorder. This is the only diagram that will survive without disorder, and this is some relatively, let's say, important for the physics, but not essential for spin glass diagram. Now, what are these loops? These are bilinear of Majoranas. These are green functions of Majoranas, so be careful, because the spin is tricky. These 2-point correlation function is just a spin, and there is going to be spins at different times, right? So every full line is a spin at different time. The wiggle line is photon, and the dotted are disordered contractions. Now, the point is that this series is controlled in S. So there are subleading diagrams in 1/S, and you are taking thermodynamic limit. And the nice thing is that the way you do this resummation, that is an Albert-Staszonovich thing, gives access to spin-spin correlation functions. So I don't expect you to understand any of this mumbo-jumbo, but if you are an expert in the audience, and I know that there are people that know what I'm talking about, I wanted to give them coordinates to have a chance to discuss more later or to ask questions, okay? And you get a coupled integral differential equations. This is what Dyson equation means. So like, it's a big mess. Maybe a message for the MO community is, can we do something simpler than this crazy stuff? Decay model. Everybody likes and understands decay model. So as I said, that's the only diagram surviving without disorder. And basically, that's a plot that you can find in our paper, where basically now the size of quantum fluctuations is not anymore S, because we have only 1 pancake and 1 photon mode. And the size, as you all know, of quantum fluctuations is N, and like we're compared with mean field, and there is also comparison with other methods that I don't show here, so it's more for advertisement purpose. So this is to say, we have written a very long 40 pages pedagogical work where we make an effort to connect to simple models, and then we go with the crazy spin glass stuff. because like we wanted to make it welcoming for the community. So if you are interested, there is something there that you can connect to stuff that you solve on an everyday basis. With that I'm done. I wanted just to say that for me, the excitement is this point in particular. So the fact that I don't know many models that you can almost semi-analytically solve, because for me, diagrammatics is basically semi-analytical, right? I mean, solving integral differential equation on computer, I mean, I would not call it numerical method. So normally to say when the quantum to classical crossover happens, you have to do phenomenological arguments, you have to wave your hands, you have to open booking quantum mechanics that will give you some very and wavy things. So that's what makes me excited about this, and I think this can be exported to many other models. There are other signatures of glasses that are things that I will let here for your questioning, and thanks for your attention.
So thanks for the interesting talk. So I have a kind of question. So in at least like classical spin glasses, which is kind of mappable to connected networks, there is this kind of like the limit cycle phases that may emerge in time. So do you think that something similar of that sort would happen? So although you do not have any order in a space, you may have like repetitive pattern in time?
So I want to answer in a fun way. At the very beginning of the project, like always, we didn't know what we were doing, like everyone, right? When you start something, you have no idea what you're doing. We were omitting some of these diagrams, and we're getting completely spurious periodic cycles. And we're saying, what's this? I mean, like I never thought. So I never see, when I do the proper resummation, I never see limit cycles. Mm-hmm. And frankly, I don't know of anyone reporting that, but the only thing I can tell you, if you do it wrong, in an intelligent way, I can show you limit cycles from 1 year ago results, which is wrong though. So I unfortunately have no physics answer to that. I don't think it would or should. Do you have an argument why should that happen in frustrated systems?
Well, no. I mean, first, I also kind of like admit that it's kind of quite fragile. I only know like a few like system which is kind of like protected by some symmetry. The gap is protected, so then the limit cycle would be like not only just the classical in the phase space, but also in quantum sense, then it is robust. So, but then I think that the reason that I was kind of quite interested in also like the emergence of like a out of time order correlations that might have also some implications in terms of like the limit cycle. I would be kind of interested in discussing.
But
further.
I want to make a maybe comment with a provocative thing, maybe for the workshop when we continue. So I am not sure for a true many-body system. No, so not something mean field, not something collective. Mm-hmm. So an honest many-body system with plenty of excitations, okay, and dissipation and inhomogeneous interactions. I don't know one example of many-body quantum limit cycles. So I don't know. I mean, maybe someone can contradict me, but I repeat my ingredients. I have inhomogeneous interactions. I have strong dissipation. The system is truly many-body, so I cannot write it as a big spin. I cannot mean fieldish-ize it. I don't know of any stable.
There are very kind of handful of them. But for example, one example that we investigated is that if you have a strong symmetry, then but what happens is that if your system is kind of Markovian, what happens that in addition to the kernel that you always have in a system, you would only have like a handful of poles on the imaginary axis, then that's basically kind of what your limit cycle.
Maybe we should continue later, but sure. I'm very curious to see this system because sure, symmetries can protect, they can do that, but like in a truly many-body situation, I would be very curious to.
Sure, yeah, I think that we can kind of discuss that in details. Yeah, thank you.
Very nice, Jamir, very exciting. One question is regarding the method.
Yes.
When you use the two-particle effect to PI method, you have to typically include non-Markovian terms, the memory integrals. Are they including there?
They are there, yes. They are there. That's these memory effects are essential that I'm writing here. These are our retarded interactions, right, happening at different times. and you are examining the full series of them. So memory is vital, because spin glass will not happen if you don't have memory, right? It's all about aging, remembering. So that's essential. If you want, it's a way to do non-Markovian.
And how do you know that you are converging then? Because 1/n is the expansion parameter, and
I know that we are not immediately wrong. Of course, I mean, Anna Maria raises a good point, right? So because these are very intractable problems, when you go down to spin 1/2, there is no benchmark. There is no ED, there is nothing. The thing that, however, for me is really honestly a shock, or maybe a certification of the merit of Hossein, I don't know how I should phrase it, is that, you see, the 2pi, that is the blue line, is perfectly on top of DTWA, what we did, for very large speed systems. And this is at least a signature of the fact that we didn't screw up anything obvious in the resummation. There is no factor 2, there is no wrong minus, there is no missing symmetry ingredient. You will not get such nice agreement of 2 empirical methods, because these are 2 empirical methods. They don't have a strong control parameter to match on top of each other. And this is happening at spin 20. It's not at a spin 100, 1000. Then how do I know that I am ultimately correct at spin 1? I don't. These are intractable problems, and that's the frontier. But at least we didn't screw up a factor 2. That's for sure. Otherwise, you will never get this crazy agreement.
Really fun talk, interesting results. So if you did eliminate the photon field and ask the same questions, would you get complete nonsense? Would you get how crucial was it in all of these results to keep the photon field dynamical?
Right. So I have so many ways to answer. It depends how much you crave for dinner. I think not, because... No. I'm Italian. I think I can handle creative jokes. Okay, so this is a little bit the dependence of the photon frequency and order parameter. So what you can ask, so this is the limit of adiabatic elimination, right? So this is frequency of photon being way larger than the typical energy scales of the atoms. And all the results basically probably lie around here. So in actuality, the active photon is more a way to protect ourselves from this, let's say, big and growing number of papers criticizing atoms only. It's more maybe paranoia of us, or show off of muscles. We want to keep the photons. But perhaps there is physics, because at resonance, you can ask who is going to win. If the enhancement of interactions, because of course, as you reduce the detuning, interactions grow stronger, as you know, or maybe the internal heating, coming from the fact that now you have resonant exchange of excitations, and so this thing can destroy your order. And perhaps again, reassuring, we get very similar picture that we got with James and Anna some time ago for a simpler model. Actually, at resonance, you have a bump of order. So this is Edwards-Anderson order parameter, and it peaks at resonance. So maybe keeping the active photons is interesting, because it shows that there is a convenience. In general, it's never clear, right, beyond the adiabatic elimination, what you're going to get, if only mess or something interesting. Actually, that's the actual data that we recollect, just for clarity. And it's nice that in a simpler model, we were seeing qualitatively, of course, the same story. So I tend to believe that this is true.
Thanks.
Also, a very naive question. So you have, like you said, the M, the big M was the number of modes in the cavity. So there are many of them. It was like 1,000 or so. So then, I mean, why, if I would do it in free space, why is it crucial, the cavity? Because you control the M, or
no? No, it's very important to, of course, for all the reasons you do cavity. So you want a controllable interactions. The shape of these modes that gives you this effective disorder is very important. Now you can ask me technically, can you repeat the cell calculation in free space, okay? And the answer is yes. So for technical reasons, 2pi will equally be hardly working in that regime. You will have to hardware a lot, to work a lot and hard, but you will be able to do it. But the physics is completely different, right? Because this network with tunable interactions, disordered depending on the shape of the modes, this cosinus, Ri times Rj that I was showing in Stanford, that thing will not arise in free space. So if you do the calculation, I mean, it's not the same. But technically, there is no obstacle. So if you look at the problem as a theoretician, but there will not be spin glass. There will be something else. It's the model of Anna and Derek, right? In free space. It's very similar, actually, to the model of Dana and Derek, right? Somehow in free space.
Yeah, that's what I was asking.
It is, right? Where is Anna? It's there, yes.
I mean, if the cavity is open, of course. If it's closed, then not. Okay, last question?
Yeah, maybe connected to that. So then, like in subradiance, when you have subradiance, you can also have this kind of very slow metastable tails. So is this kind of subradiant power law tails connected to this aging in a spin glass, or, I mean?
So there is perhaps a subject for discussion during the workshop. So very long time ago, we were asking about the, let's say, strong dissipative or bad cavity limit of this model, where now you will have jump operators that are frustrated, right? So if you imagine that kappa is very large and you do the usual adiabatic elimination, you're going to get a correlated dissipator like the ones that I like to study with frustrated dissipative interactions. And then you can ask there, is there anything interesting? At the time, we didn't have the muscles to solve that problem. Or if I want to be, again, flattering to my students, I didn't have the student to solve that problem. I don't know. It's something I was asking myself a long time ago, and then I got interested in other things. So these are projects on long time scales, and my interest span, unfortunately, fluctuates. It's an interesting question. The point is that it's not due probably to subradiance, because these things, these low tails that you are talking about in aging, they appear also for very weak dissipation. In principle, also for zero dissipation. So if you start with the right low energy state. So I have to exclude that this frustrated dissipation is doing anything. Now, if you exaggerate with kappa, you kill spin glass, and you have a completely new problem.
That's the thing, like you have something like a dissipative spin glass.
Yeah,
it's an abuse of language.
I don't believe in effective dissipative interactions, but certainly it's an interesting problem, for sure. And it would be very hard to solve, way harder than this, and maybe there is rich physics. And maybe someone wants to pick up on that, or we can talk about it. I'm very open. You could solve it, I have no idea, but I would exclude that that type of subradiance, that type of correlated dissipation is playing a role in these tails, because I see them a very weak dissipation as well. So.
All right. Let's